For the second part of part 2 in the notes here, we're going to go through Hess's law. For this, basically what you're trying to do is go through a puzzle. So if you look here, right in here, this is the answer that you're looking for right here. Okay. So what that means is you need 4 aluminums and 3 manganese oxides to be the reactants. You need 2 aluminum oxides and 3 manganese to be the products. So what you have to work with are these puzzle pieces down here. You're going to need to multiply, divide, flip, anything necessary to get things to where they need to go. So the easy way to do this is just pick something and go. Typically, if you notice that something is in multiple equations, like in this instance, there's oxygen in both the top and the bottom equation, just kind of ignore it and do everything else first, and they tend to work themselves out. So for this one, you notice how it says 4 aluminum and it needs to be a reactant. If you look down here, we have 2 aluminums as a reactant in the top equation. So in order to get to 4, you're obviously going to have to multiply by 2. When you multiply by 2, you're going to multiply everything in that equation by 2 and delta H by 2. And I'm just going to rewrite this out down below here. 4 aluminum plus 3 oxygen gives you 2Al2O3. And delta H also gets multiplied by 2, so that is negative 3352. It's in kilojoules. I'm just not going to write out the units right now. So that takes care of the 4 aluminums. The next thing it says is 3 manganese oxides needs to be on there. So we look down at the bottom equation that has manganese oxide in it. There's only 1 and it's a product, and we need 3 and to be a reactant. So what we need to do is multiply this by negative 3. The negative will flip the equation from a synthesis to a decomposition. And the 3 obviously multiplies by 3. So what that does is it makes it 3MnO2. Gives me 3Mn plus 3O2. Delta H equals, remember we're multiplying that by negative 3, so positive 1560. So now what we need 2Al2O3 to be a product. If we look down here at our new equations, we have 2Al2O3 as a product. And we need 3Mn to be a product. And again, we look down here and we have 3Mn being a product. So what we can do now is cancel out anything that is on both the left and the right side of the arrows using both of these equations that are down here. So if you notice, there are 3 O2s that can go away on both sides. And what we're left with is 4Al plus 3MnO2 gives you 2Al2O3 plus 3Mn. So just like we added the 2 equations together, because what Hess's law says is that equations happen in steps, we can add those steps together. So we can not only add together products and reactants, but we can also add together the enthalpies of formation, or the delta H's. So when we do that for this equation, delta H is negative 3352 plus positive 1560, which is negative 1792 kilojoules. So that's our first example with Hess's law. I'm going to skip over extra problem number 1 and we're going to go to extra problem number 2 here and just do another Hess's law example. Again, that top thing is what we're looking for. So we need 1 CH4 to be a reactant, and we look down here, CH4 is only in the second equation and it is a product. So we need to multiply this by negative 1. You can rewrite out the equations down below if you'd like to. So if you want to write CH4 gives you C plus 2H2, delta H is positive 74.9. You can, if you recognize what's going on by just multiplying up top in these equations that are given, that's fine too. The next thing, we need 1 NH3 to be a reactant. We have 2 that are a product, so we need to flip it and divide by 2. So it's multiplying by negative 1/2 for everything. So that's going to give us NH3 giving us, because remember we flipped it, 1/2 N2 plus 3 halves H2. Delta H is going to get multiplied by negative 1/2, so that's 45.9. My bad. 45.9. The last thing here, we need HCN to be a product. We have HCN as a product, but we need only half that, so we're going to divide by 2 as well here. So we're left with 1/2 H2 plus C plus 1/2 N2, giving us HCN delta H equals 270.3 divided by 2, which is 135.15. So now if we're looking through here, you notice H's are in every equation. So we're just going to assume that's going to work itself out. So let's look for anything that can cancel out. You have a 1/2 N2 that's on the left, a 1/2 N2 that's on the right. You have a C that's on the right, a C that's on the left. You have 1/2 H2 and 3/2 H2. So I'm going to get rid of the 1/2 and I'm going to get rid of this, and that would just be 1 because we got rid of 1/2. So what you're left with is CH4 plus NH3 gives you HCN plus 3H2, which is exactly what we were looking for. The delta H value then, you just add those all together and you get 255.95. So that's Hess's law. That's what we're going to be doing in the lab on Thursday. Is you're going to be doing 3 different reactions and trying to see if the parts add up to the total reaction like they should. Another way to solve for delta H for a reaction is to use the heat of formation, or the standard enthalpy of formation. You can notice down here where it says standard enthalpy of formation, you have delta H with a degree sign and F, and all the degree sign means is that at a standard state, so standard temperature and pressure, which is usually 1 atmosphere and 25 degrees Celsius, or 298 Kelvin, that's the heat that is either created or released or absorbed based on the formation of that individual thing. One change from your notes is in the notes it says to reference a page in your book, and that's from our old textbook that I forgot to change out. So what you're going to want to do is look in the appendix in the back of your book. I forget which page it is exactly because they have kind of weird numbering back there, but look for an appendix that has a bunch of delta H values. Usually it'll have delta S values with it as well, so you'll kind of know you're in the right place if you start seeing some of those. So what you need to do in this, first thing here says just write a thermochemical equation that shows this. So you want to show the formation of SiCl4 liquid. So if we guess what makes SiCl4, I'm guessing most of you could come up with Si and Cl, which chlorine in its elemental form is Cl2, and there'd be 2 of them to balance out the equation. And all the thermochemical equation would say is that delta H equals -687. So what you would do is you'd go to the back of the book, go to the appendix, and what you would find is that silicon, any element by itself, has a formation of 0 because it doesn't take any heat to form an element. Same thing here would be 0, and this would be -687. So we can create this thermochemical equation either by being given it, or Hess's law, which we just did, or by doing the heats of formation from the back of the book. In order to solve for the heat of formation, you can see the equation that we have here. It's delta H equals the sum of the H's of the products minus the sum of the reactants. So it's just products minus reactants. We're going to go look up those values, add them all up. Notice how there's N and M there. N is the number of moles of products in the balanced equation. M is the number of moles of reactants. So we'll show that here in a couple examples. For the first example here, it says calculate the heat of vaporization of water. So heat of vaporization of water is when we go from a liquid to a gas. So we're going from H2O liquid to H2O gas. Not really an equation, it's more of a phase change, but this is how you can calculate out how much heat you need to add to water to get it to go from liquid to the gas phase. So you'd go to the back of your book, to the appendix, and look this up. This is 285.8. And this one is -241.8. Notice those are both exothermic. That's what the negative means. So in order to solve for what is the heat of vaporization, you say -241.8, that's the sum of your products, minus the sum of your reactants, -285.8. So we're subtracting a negative, so we're adding here, and we get a positive 44 kilojoules. Which means that when we go from a liquid to a gas, it's endothermic, which should make sense because you have to absorb energy to get the molecules moving faster to go from a liquid to a gas. For the final thing here, we have an equation given to us, and you're going to have to go look up these values. Obviously, I did this for you, so this is 33.1. You went and looked it up. This is -285.8, same as it was in the example above. This is -207.4. and this is 90.29. So sum of the products minus sum of the reactants, and you remember the N and the M, you're going to multiply it by how many there are in the balanced equation. So, sum of my products. There are two HNO3s, each with a heated formation of 207.4. Again, that just means how much is released when that forms. Plus, there's one NO at 90.29. So that's the sum of my products, minus sum of my reactants. There are three NO2s, each with a heated formation of 33.1, plus one H2O with a negative 285.8. Oops, 285.8. So you're going to plug that all in your calculator or do it in your head if you really feel like that. Negative 138 kilojoules. As long as you use the numbers in the back of the book, it should be pretty straightforward how to do those. We'll go through this in class on Thursday, make sure we're all set. We'll have plenty of time in order to do the lab because we're going to kind of work together and have different people do different parts of that so we can get good data. So if you have any questions as you're going through this tonight, make sure to just email me. I'll help you out. Otherwise, we'll go through it in class on Thursday.